This video demonstrates the operation of an incorrectly wired grounded control transformer circuit. Motor control circuits can be the same voltage as the motor up to 600 volts or can be reduced by means of a control transformer. Where one side of the motor control circuit is grounded, the design of the control circuit must prevent the motor from being started by a ground fault in the control circuit wiring. This rule must be observed for any control circuit that has one leg grounded. This circuit simulates the dangerous effect of an incorrect ground connection. In this case, one side of the start button is in the ground leg of the circuit. As a result, a ground fault that occurs on the coil side of the start button will short circuit the start circuit and start the motor. This video demonstrates the operation of a correctly wired grounded control transformer circuit. In contrast to the incorrectly wired control circuit, the starting of the motor by an accidental ground fault is effectively eliminated. In this instance, the ground fault creates a short circuit that causes the main circuit breaker to trip rather than having the motor start. This video demonstrates the operation of an across-the-line starter with additional start-stop connections. When one of the starts buttons is pressed, coil M energizes to close all M contacts. The M contacts in series with the motor close to complete the current path to the motor. These contacts are part of the power circuit and must be designed to handle the full load current of the motor. Memory contact M, connected across the start button, also closes to seal in the coil circuit when the start button is released. This contact is part of the control circuit. As such, it is required to handle only the small amount of current needed to energize the coil. The starter has 3 overload heaters, one in each phase. The normally closed relay contact OL opens automatically when an overload current is sensed on any phase to de-energize the M coil and stop the motor. The motor can be started or stopped from 2 locations. Additional start buttons must be connected in parallel with each other, and additional stop buttons in series with each other. This video demonstrates the operation of timed starting of 2 motors. The circuit has been designed so that there will be a short time delay period between the starting of motor 1 and motor 2 to reduce the amount of starting current. The first motor is started by pressing the start button connected in a 3-wire control configuration to motor starter M1. Power is applied to both motor 1 and an on-delay timer coil TR. After the 10-second time delay period, the normally open time contacts on TR close to energize starter coil M2, and the second motor is automatically started. Both motors can be stopped by pressing the stop button. This video demonstrates the operation of a hand-off auto motor control circuit. The function of a hand-off auto, or HOA circuit, is to control whether a motor is in the hand, manual mode, auto mode, or off. With the selector switch in the off position, both contacts A and B are open, preventing operation in both manual and automatic modes. With the selector switch in the manual position, contact B is closed while A remains open, allowing for operation in the manual mode only. With the selector switch in the auto position, contact A is closed while B remains open, allowing for operation by the thermal switch in the auto mode only. This video demonstrates the operation of a motor control circuit interlocked so that motors are required to be turned on in the correct sequence. The circuit has been designed so that the three motors must be turned on manually in the order 1, 2, 3. The auxiliary normally open contact M1 from the first starter is connected in series with the stop button of the second starter. The auxiliary normally open contact M2 from the second starter is connected in series with the stop button of the third starter. As a result, motor 2 or 3 will not be able to be turned on without the previous motor starter being energized. If motor 1 is turned off, then all three motor starters will be de-energized. This video demonstrates the operation of a motor control circuit connected so that motors are connected to automatically turn off in sequence. This simulation is an application of how this is applied to a two-stage motor conveyor system. When the start button is momentarily closed, starter coil M1, starter coil M2, and timer TR are energized. Both motors start at the same time. M1 normally closed contact opens to open the circuit to the horn. TR normally open timed open contact closes to keep starter coil M2 energized. When the stop button is activated, motor M1 stops immediately, but motor M2 continues to operate until the time delay period has elapsed. The warning siren comes on and remains on at all times that motor M2 is running and motor M1 is not. This video demonstrates the operation of an emergency stop control circuit. Emergency stop switches are used to ensure the safety of persons and machinery. This application simulates the operation of a two-starter motor control circuit that includes an emergency stop push button. The emergency stop function is initiated by a single human actuation of the e-stop button. When activated, both motor starters drop out or de-energize regardless of their original state of operation. Both starters will remain de-energized until the e-stop is reset manually. To reset the e-stop, the actuator must be manually unlatched with a twist or a key release. The e-stop itself does not restart the motors, it only permits restarting through normal procedures, appropriate for the process involved. This video demonstrates the operation of a primary resistance starter. Reduced voltage starting is obtained in the primary resistance starter by means of resistances that are connected in series with each motor's stator lead during the starting period. The voltage drop in the resistors produces a reduced voltage at the motor terminals and in turn reduced starting current. Pressing the start push button energizes motor starter coil M and timer coil TR. The motor is then started through a resistor in each of the three incoming lines. After a time delay period of 5 seconds, the timer on delay contacts closed to energize the run contactor coil. This causes contacts R to close, shorting out the resistors and applying full voltage to the motor. The resistor's value is chosen to provide adequate starting torque while minimizing starting current. This video demonstrates the operation of a Y-delta starter. Y-delta starting involves connecting the motor windings first in a Y during the starting period, and then in delta after the motor has begun to accelerate. Connected in a Y configuration, the motor starts with a significantly lower inrush current than if the motor windings had been connected in a delta configuration. When the start button is pressed, contactor S coil is energized. The S main power contacts close to connect the motor windings in a Y configuration. The normally open S auxiliary contact closes to energize timer coil TR and contactor coil M1. The M1 main power contacts close to apply voltage to the Y connected motor windings. Normally open auxiliary contacts S and M1 close to seal in and maintain the timer coil TR. After the time delay period has elapsed, the TR contacts change state to de-energized contactor coil S and energized contactor coil M2. S main power contacts, which hold the motor windings in a Y arrangement, open. The M2 contacts close and cause the motor windings to be connected in a delta configuration. The motor then continues to run with the motor connected in a delta arrangement. Contactors S and M2 are electrically and mechanically interlocked so that both contactors cannot be energized at the same time, as this would result in a line-to-line short circuit. This video demonstrates the operation of an across-the-line DC motor starter. It operates as a standard 3-wire motor control. One major difference between AC and DC starters is the additional electrical and mechanical requirements necessary for suppressing the arcs created in opening and closing contacts controlling a DC motor load. To combat prolonged arcing and help extinguish the arc, this starter is equipped with 3 power contacts connected in series. This video demonstrates the operation of a 3-phase reversing starter operated with a faulted mechanical interlock. When the motor is reversed, it is vital that both the forward and reverse contactors are not energized at the same time. Activating both contactors would cause a short circuit since 2 of the line conductors are reversed on one contactor. Mechanical interlocking is normally factory installed and uses a system of levers to prevent both contacts from being energized at the same time. Energizing the coil of the forward contactor moves a lever in such a way as to physically block the movement of the reverse contactor. Even if the reverse contactor coil should become energized, the contacts will not close because the mechanical interlock is physically blocking the reverse contactor. The forward contactor coil must be de-energized before the reverse contactor can operate. The same applies if the reverse contactor is energized. For this scenario, the mechanical interlock has been assumed to have failed to operate properly. As a result, when both the forward and reverse contactors are energized at the same time, a short circuit is created which trips the circuit breaker. This video demonstrates the operation of a reversing starter with electrical interlocking via starter's forward and reverse auxiliary contacts. The normally closed auxiliary contact controlled by the forward coil is connected in series with the reverse coil. The normally closed auxiliary contact controlled by the reverse coil is connected in series with the forward coil. When the forward coil is energized, the normally closed contact in series with the reverse coil is open to prevent the reverse coil from being energized. When the reverse coil is energized, the normally closed contact in series with the forward coil opens to prevent the forward coil from being energized. To reverse the motor with this control circuit, the operator must press the stop button to de-energize the respective coil, reclosing the respective normally closed contact. Reversing starters are usually factory wired for electrical interlocking. This video demonstrates the operation of a reversing starter with push-button interlocking. Electrical push-button interlocking utilizes break-make normally closed and normally open switch contacts on the forward and reverse starter buttons. Interlocking is achieved by connecting the normally closed contact of the reverse button in series with the normally open contact of the forward push button. The normally closed contact of the reverse push button acts like another stop push button in the forward circuit. The normally open contact on the reverse push button is used as the start button for the reverse circuit. When the reverse button is pressed, the normally closed contact opens the circuits to the forward coil, then its normally open contact completes the circuit to the reverse coil. When the forward button is pressed, its normally closed contact opens the circuit to the reverse coil, and then its normally open contact completes the circuit to the forward coil. The motor reverses direction immediately without the stop button being pressed. Push-button interlocking is used in conjunction with both mechanical and auxiliary electrical interlocking and is intended to supplement these methods, not replace them. This video demonstrates the operation of a reversing starter with limit switch travel control. Limit switches can be used to limit the travel of electrically operated doors, conveyors, hoists, and similar devices. Pressing the forward push button energizes the FWD coil. Auxiliary memory contact F closes to seal in and maintain the forward coil. Auxiliary interlock contact F opens to isolate the reversing circuit. Power contacts F close and the motor runs in the forward direction. If either the stop button or forward limit switch is actuated, The holding circuit to the FWD or forward coil opens, de-energizing the coil and returning all F contacts to their normal de-energized state. Pressing the reverse push button energizes the reverse coil. Auxiliary memory contact R closes to seal in and maintain the reverse operation. Auxiliary interlock contact R opens to isolate the forward coil circuit. Power contacts R close and the motor runs in the reverse direction. If either the stop button or reverse limit switch is actuated, the holding circuit to coil REV, or reverse, opens, de-energizing the coil and returning all R contacts to their normal de-energized state. The location of the limit switches in the circuit allows the one direction of travel to be stopped if the motor is driving a device that has limits to its travel. The opposite direction is not affected by one travel limit being reached. As soon as the direction of the motor is changed and the actuator is no longer holding the limit switch open, it will return to its normally closed position. This video demonstrates the operation of a reversing starter with limit switch control in a reciprocating machine process which requires a repeated forward and reverse action. The start and stop push buttons are used to initiate and terminate the automatic control of the motor by limit switches. Contact CR1 is used to maintain the circuit to the control relay during the running operation of the circuit. Contact CR2 is used to make and break the line circuit to the forward and reverse control circuit. Using the control relay and its start and stop push buttons also provides low voltage protection. That is, the motor will stop when there is a supply voltage failure, and the motor will not restart automatically when the supply voltage is restored. The normally closed contact of limit switch LS2 acts as the stop for the forward controller, and the normally open contact for limit switch LS1 acts as the start contact for the forward controller. The auxiliary contact of the forward starter is connected in parallel with the normally open contact of limit switch LS1 to maintain the circuit during the running of the motor in the forward direction. The normally closed contact of limit switch LS1 is wired as a stop contact for the reverse starter, and the normally open contact of limit switch LS2 is wired as a start contact for the reverse starter. The auxiliary contact on the reverse starter is wired in parallel with the normally open contacts of limit switch LS2 to maintain the circuit while the motor is running in reverse. Electrical interlocking is accomplished by the addition of a normally closed contact in series with each starter and operated by the starter for the opposite direction of rotation of the motor. Reversal of the direction of the rotation of the motor is provided by the action of the limit switches. When limit switch LS1 is moved from its normal position, the normally open contact closes, energizing coil F, and the normally closed contact opens and drops out the reverse coil. The opposite action is performed by limit switch LS2, and thus reversing in either direction is provided. The forward and reverse push buttons provide a means of starting the motor in either forward or reverse in order that the limit switches can take over automatic control. This video demonstrates the operation of a push-button jog circuit. Jogging is the momentary operation of a motor for the purpose of accomplishing small movements of the driven machine. The push-button jog circuit uses a standard start-stop control circuit with a double contact jog push button, one normally closed contact and one normally open contact. Pressing the start push button energizes starter coil M, causing the M main contacts to close to start the motor and the M auxiliary contact to close to maintain the M coil circuit. When the M coil de-energized and the jog push button pressed, the circuit is completed for the M coil around the M auxiliary maintaining contact. The M main contacts close to start the motor, but the maintaining circuit is incomplete as the normally closed jog contact is open. As a result, starter coil M will not seal in. Instead, it can stay energized only if the jog button is fully depressed. On quick release of the jog push button, should its normally closed contacts reclose before the starter maintaining contact M opens, the motor would continue to run. In certain applications, this could be hazardous to workers and machinery. This video demonstrates the operation of a control relay jog circuit. The control relay jogging circuit is much safer than a straight push-button jog circuit. A single contact jog push button is used along with the jog control relay. Pressing the start push button completes a circuit for the CR coil, closing the CR1 and CR2 contacts. The CR1 contact completes the circuit for the M coil, starting the motor. The M maintaining contact closes. This maintains the circuit for the M coil. Pressing the jog button energizes the M coil only, starting the motor. Both CR contacts remain open and the CR coil is de-energized. The M coil will not remain energized when the jog push button is released. This video demonstrates the operation of a start-stop selector jog circuit control. The start button doubles as a jog button. When the selector switch is placed in the run position, the maintaining circuit is not broken. When the start button is pressed, the M coil circuit is completed and maintained. Turning the selector switch to the jog position opens the maintaining circuit. Pressing the start button completes the circuit for the M coil, but the maintaining circuit is open. When the start button is released, the M coil is de-energized. This video demonstrates the operation of jogging a three-phase reversing starter using a jog-run selector switch. When the jog-run switch in the run position, the circuit operates as a reversing starter with electrical interlocking of the forward and reverse starter coils in addition to the forward and reverse push buttons. When the jog-run switch is in the jog position, the jogging function is initiated through the selector switch by opening the seal-in circuit to both the forward and reverse starter coils. This video demonstrates the operation of an anti-plugging motor protection circuit. Anti-plugging protection is obtained when a device prevents the application of a counter torque until the motor speed is reduced to an acceptable value. This sudden reversing torque applied when a large motor is reversed could damage the driven machinery, and the extremely high current it results in could affect the distribution system. This simulated anti-plugging switch circuit prevents the application of a counter torque until the motor speed is reduced to an acceptable value. Pressing the forward button completes the circuit for the forward coil, closing the F power contacts and causing the motor to run in the forward rotation. The F0 speed switch contact opens because of the forward rotation of the motor. Pressing the stop button disengages the forward coil, which opens the F power contacts, causing the motor to slow down. Pressing the reverse button will not complete a circuit for the reverse coil until the F0 speed switch contact recloses as the motor slows down. As a result, when the rotating equipment reaches near zero speed, the reverse circuit may be energized and the motor will run in the reverse rotation. This video demonstrates the operation of timing relays used in an anti-plugging circuit. Off-delay timers are connected in parallel with the forward and reverse contactor coils of the reversing starter. The normally closed time closed contact from the forward timer coil, TD1, is interlocked with the reversing circuit. The normally closed time closed contact from the reverse timer coil, TD2, is interlocked with the forward circuit. When the motor is started in the forward direction, the timer coil TD1 is energized at the same time as the forward coil. The relay contact TD1 opens immediately in the reverse coil circuit, as does the auxiliary F interlock. When the stop button is activated, both the F coil and the TD1 coil are de-energized. The F interlock returns to normally closed state. However, the TD1 interlock remains open for an additional 8 seconds before returning to its normally closed position. As a result, the reversing coil R cannot be activated until the drive motor has been allowed 8 seconds to come to a stop. The timing relay TD2 provides the identical action in the reverse coil operation. This video demonstrates the operation of dynamic braking as applied to a DC motor. Dynamic braking is achieved by reconnecting the running motor to act as a generator immediately after it is turned off, rapidly stopping the motor. With the motor operating, the stop button is pressed. Starter coil M energizes to open the normally open M power contact to the motor armature. At the same time, the normally closed M power contact closes to complete a braking circuit around the armature through the braking resistor, which acts like a load. The shunt field winding of the DC motor remains connected to the power supply. The armature generates a counter EMF voltage, which causes current to flow through the resistor and armature. The smaller the ohmic value of the braking resistor, the greater the rate at which the energy is dissipated, and the faster the motor comes to rest. This video demonstrates the operation of DC injection braking applied to an AC induction motor. DC injection braking is a method of braking in which direct current is applied to the stationary windings of the AC motor after the applied AC voltage is removed. The injected DC voltage creates a magnetic field in the motor stator winding that does not change in polarity. This constant magnetic field in the stator creates a magnetic field in the rotor to produce the braking effect. The DC injection voltage is obtained from the rectified AC line voltage. Pressing the start button energizes the starter coil M and off-delay timer coil TR. Normally open M1 auxiliary contact closes to maintain current to the starter coil, and normally closed M2 auxiliary contact opens to open the current path to braking coil. Normally open off-delay timer contact TR remains closed at all times while the motor is operating. When the stop button is pressed, starter coil M and off-delay timer coil TR are de-energized. The braking coil becomes energized through the closed TR contact. All B contacts close to apply DC braking power to two phases of the motor stator winding. The braking coil is de-energized after the timer times out. The time contact is adjusted to remain closed until the motor comes to a complete stop. A transformer with tapped windings is used in this circuit to adjust the amount of braking torque applied to the motor. The motor starter M and braking contactor B are mechanically and electrically interlocked so that the AC and DC supplies are not connected to the motor at the same time.